Presenting our research work TENET, which is a memory safe and fault tolerant persistent transaction memory. In this work, we tackle a very important problem of how to protect your NVM data from software bugs and media errors, right? NVM has been there for quite some time now, and researchers have been building a lot of in-memory applications by exploiting its byte addressability and non-volatility. But the important thing here is the byte addressability of NVM is basically enabled by mapping the NVM address to the user space, so that the application can use simple load store instructions to access the NVM region. And this makes NVM data actually vulnerable to data corruption due to application bugs. Let's say, for an instance, an application has a memory safety bug, a buffer overflow. It can directly go ahead and just corrupt the NVM data, and since NVM is non-volatile, the data corruption is persistent forever, right? And this is not just the only cause for the concern for us here. There are also other class of errors that happens on the hardware side, which is called media errors. Generally, the media errors can happen in the NVM media due to several reasons, but some reasons are due to the device. As the device gets older and it wears out, and there are some power spikes, right? And whenever an hardware or the media error happens, the NVM it can corrupt a random NVM offset, and the offset where this particular NVM page belongs to is completely lost, right? So with these two problems in mind, we ask ourselves two questions. So first, how to detect memory safety bugs in the application, and also to prevent it from corrupting the NVM data. And although it is not completely possible to prevent the media errors, we ask ourselves, how do we prevent data loss in the event of a media error, right? And we propose TENET as a solution for both the questions. Before we move on to the design details of TENET, we'd like to cover some background on NVM memory safety errors, right? Generally, the memory safety violations or software bugs are classified into two types: spatial safety and temporal safety violation. A spatial safety violation happens when a buggy application tries to access a memory region beyond its allocated range. In this example, the buggy memcopy is trying to overwrite a buffer, and this is a classical spatial safety violation example. And a temporal safety violation happens when there is a dangling pointer. In this example, application is freeing the buff while there is a live reference in the code. So whenever the pointer is used again by the application, it leads to use after free or a use after free realloc, depending on the scenario, right? And both these spatial and temporal safety violations are pretty common in low-level C, C++ programs, and NVM applications written in such programming languages are no exception to these bugs as well, right? And on the other hand, we have the media errors. Two types are correctable and uncorrectable. Correctable media errors are not a cause for concern because they are transparently detected as well as corrected by the hardware ECC. On the other hand, uncorrected hardware or the media errors are something that the hardware ECC cannot correct itself, so the onus falls on the application to fix the corrupted NVM page. So with that respect, the application needs to have some kind of a backup of the NVM data in order to roll back the corrupted NVM page, right? So that's the case of uncorrectable media errors, right? There are very few works that tackle the memory safety and fault tolerance problem in the NVM compared to the other areas of NVM research, right? And most of the prior works basically add some sort of memory safety or a fault tolerance capability to the libpmem obj, which is a PMDK's transaction library, right? We will come back to this table a little bit later in the talk, but one thing that I would like to highlight from this table is guaranteeing memory safety and fault tolerance at a lower performance overhead and a cost is a very challenging problem, and this is something that we try to do in TENET, right? Yeah, so what is TENET? TENET is basically an NVM programming framework which helps developers to build memory safe and fault tolerant NVM data structures and application around this data structure, right? And we have two goals. We want to protect NVM data from buggy application code by guaranteeing basically spatial and temporal safety. Then TENET aims to guarantee a performance and cost efficient fault tolerance to guarantee to protect NVM data from uncorrectable media errors. In our model, we do not consider adversarial attacks, right? And we consider the TENET library code, the core library code, and the OS kernel as a part of trusted computing base, right? Since TENET is a programming model, it needs programming framework, it needs some sort of programming model, and in that regards, we support persistent transactions, right? Instead of reinventing a new transaction system, we adopt one of the existing transaction system or the PTM called Timestone. The reason we adopt Timestone is because of its high scalability and performance, right? And I would also like to highlight here that the Timestone is neither supports memory safety nor fault tolerance. It's just a baseline transaction for us to build our TENET safety techniques. So one of the fundamental design principles in TENET design is to prevent application code or any code outside of the TENET library from writing directly to the NVM. In our framework, only TENET library code is allowed to perform direct NVM writes. So why do we have to take such measures? Let's take a look at an example. Let's say a buggy application code wants to write to a buffer in the NVM, and as you can see, this is a buggy code. It's going to cause buffer override, and when the buffer overrun happens, it is not only corrupting the buffer but also some of the NVM objects in the adjacent memory space. And to make things worse, readers can also read, are in danger of reading the corrupted data, right? So in order to prevent this, we make NVM read-only for the application code, right? And we enforce this read-only permission for the NVM region using MPK, which are the memory protection keys, which is a hardware primitive available in the Intel systems, right? So now when an application code, whether it is buggy or non-buggy, when it tries to write to an NVM pool, it receives an exception that it cannot write to it. And what it essentially entails is readers now can read the NVM object without any confusion or without any need for validation to check whether the objects that they read are corrupted or not corrupted. This is a this is very important in order to get better performance, because prior works suffer from high performance overhead because they need to check every single NVM access to see whether the object that they read is a valid object or a corrupted object. In our case, since NVM is read only, we don't need readers to check, perform such checks, right? And these things aside, then how does even application write to NVM object? For that, application basically writes to NVM object via DRAM object, right? So application can, in this case, wants to update node B, it copies the DRAM object, and then it makes its update on the DRAM, and once the update is done, TENET basically will validate the DRAM object for spatial safety violation and writes back only the valid objects to the NVM, right? And the next obvious question is, how does this validation happen, right? And for that purpose, TENET basically uses canary bits. So basically 8-byte canary bits are assigned at the boundary of every DRAM object at the time of its creation, and after that the application is allowed to perform its write operation. And in this case, writes is buggy. So let's say after the write is over, particularly during the commit time of the transaction, TENET validates the DRAM object by inspecting the canary bits, and clearly there is a spatial safety violation in this case because the canary bits are corrupted. So instead of writing back the DRAM object, TENET discards the DRAM objects, aborts and terminates the program with an spatial safety violation exception, right? So overall, the read-only NVM using MPK and canary bits together guarantees spatial safety for the NVM data, right? But the next question that we would ask is, does making NVM read-only solve all the problems and prevent data corruption completely? Of course, the answer is no. The one example is basically when an application tries to dereference NVM because it has read-only access. When it tries to read a node that is already freed, it will be dereferenced, and this is clearly a temporal safety violation. It's a use after free bug. So the question is, how does even TENET enforce temporal safety for NVM objects, right? For that purpose, we have pointer tags. Whenever an NVM object is allocated, in this case node B, it is assigned with a unique tag, right? And the same tag is also encoded in the object's pointer. So let's see how this encoding works. Let's assume that this is an example for node B's address, and we have a tag, right? The encoding is basically nothing but updating the upper 16 bits of the NVM address, right? If you observe closely, before encoding, the upper 16 bits are unused, and after we encode, basically the unused bits represents the tag, right? And overall, our pointer layout looks something like this. The bits 0 to 47 is an NVM address, and the rest of the bits corresponds to the tag. And what this essentially entails is whenever an application wants to dereference an NVM object, in this case node B, it dereferences using an encoded pointer, and therefore TENET at the time of dereference can simply compare the tag that we stored in the object, also the tag which we encoded in the object's pointer, and dereference is successful only when the tags match. In a case where application tries to dereference using a dangling pointer or an invalid NVM object, the tags won't match, and TENET can simply terminate the program, letting application know that it is using some dangling pointers, right? So far now we have seen memory safety bugs due to software errors, spatial memory safety and temporal memory safety. The next piece of puzzle is how TENET is able to guarantee fault tolerance for NVM data against uncorrectable media errors, right? For that purpose, TENET basically replicates NVM data to the SSD, essentially maintaining a backup copy. And the high-level idea here is to restore the corrupted NVM data from the SSD backup whenever an uncorrectable media error happens, right? But our replication is not just a simple dump of NVM data to the SSD. It's more than that. We carefully designed our replication to have some desirable properties like cost efficiency, right? The cost efficiency comes from the fact that we are replicating the NVM data to the local SSD, unlike the prior works, which incurs 2x cost by simply replicating to a different NVM region, right? This is a cost efficiency property. And performance efficiency is, since we are writing to the SSD, in a critical path, if we do that, then it's going to be performance bottleneck. So we take it out of the critical path, and SSD write essentially happens in the background, right? And the obvious question will be, if the writes are happening in the background, there is a inconsistency between the NVM and the SSD. So is there a chance for losing data? The answer is no. We are able to guarantee consistent lossless recovery, and we do this by having a small portion of operation log, and I will recommend you to refer to our paper for more details on how we are able to guarantee consistent lossless recovery, right? Right. So by evaluating TENET, we would like to answer two questions. How does TENET basically compare against the prior PTM works in terms of features and the performance overhead that incurs? And also we would like to evaluate TENET on how much overhead it adds over its baseline PTM system timestone, right? Does it impact the scalability, or does it cause any performance collapse? That's something that we want to see, right? For our evaluation, we use 2-socket NVM server, and we try to evaluate 2 different versions of TENET. TENET MS, which basically supports only memory safety, spatial and temporal safety to be very particular, and TENET, which supports both memory safety and fault tolerance, right? We use YCSB workloads and some micro benchmarks in our paper, but the results that I'm going to be presenting in this talk are all from the YCSB workloads, right? So this is the table that we saw in the introductory part of the talk, and overall there are 3 techniques so far, say in terms of memory safety and fault tolerant PTM, and all are extension of PMDK transaction library. libpmm OBJ-R is nothing but a simple replication support to the PMDK transaction. It will just simply replicate the NVM data to another local NVM. And SafePM is a recent extension of PMDK transaction. By adding address sanitizer support, it will support spatial safety and temporal safety, but no fault tolerance support. And Pangolin is also an extension of PMDK, where it supports spatial safety by object checksums, and it tries to actually reduce the replication cost by, instead of replicating the raw data, it uses parity to replicate, right? So it reduces the cost of the naive replication in the NVM. So it is kind of clear from the table that TENET is the only PTM here so far is able to provide both the spatial safety and the temporal memory safety, and also the fault tolerance for NVM data. But what about the performance? What is the overhead that we are seeing here for TENET? To study that, I'm presenting you the 2 figures where we analyze the performance of TENET, 2 different versions of TENET and SafePM for a concurrent hash table for a read intensive and a write intensive workload. First, let us look at the 2 different versions of TENET. The red line here is basically the memory safety only version, and the orange line is the memory safety plus fault tolerant version. If you observe closely, there is only an 8% overhead in TENET. Basically, this overhead comes from replication, right? And for a read-intensive workload, the overhead due to replication is negligible because write ratio is less, eventually replication is also less, right? So this shows the efficiency of our replication, right? And when we compare the absolute performance for in terms of SafePM and TENET, right, two different versions, we are magnitudes of order faster, right? The reason for such a high performance is not just from the techniques that we propose. As we saw in the prior slides, SafePM is an extension of libpmm obj, the PMDK transaction, and ours is an extension of timestone, right? Basically, baseline PTM for us is timestone, and timestone is already magnitudes of order faster than PMDK. So there is also the fact that that comes into the play here. So to gain more insights, because this work is about memory safety, to gain more insights, we want to compare the relative performance to see how much overhead each of the techniques add to its baseline, right? So this figure essentially conveys that idea. So what it shows is here the performance is basically normalized to their respective baseline, SafePM for PMDK and TENET for timestone, right? What this essentially tells us is when you add SafePM to PMDK transaction, how much does the PMDK is slowed down? And similarly for TENET, if you add TENET techniques to the timestone, how much it is slowed down? And the answer is TENET is basically SafePM slows down PMDK transaction by 55%, right? Whereas TENET slows down timestone by 4% for only memory safety and 12% for both memory safety and fault tolerance, right? There are several key factors of why we are able to guarantee such low overhead, right? One of the reason being our techniques does not need additional crash consistency support, right? For example, in SafePM, the SafePM needs to perform additional undo logging. This is in addition to the PMDK transaction that is already performing its own undo logging, right? So for this undo logging is necessary basically for the memory safety metadata that the SafePM maintains on the NVM. But for us, we don't need crash consistency for memory data in the sense that ours is basically hardware primitive, and sometimes most of our pointer tags, for example, and the canary bits are inlined, so there is no like a separate notion of crash consistency for memory safety metadata, right? That is one reason why we are able to perform well. And another important reason is TENET does not need to validate every single NVM access. As we saw in the first half of the talk, readers don't need to validate the NVM objects, right? But prior techniques has to validate each and every NVM access. So we are able to make redundancy checks, right? Or prevent redundancy checks, and also we do a lot of other optimization in terms of how leveraging the serializability guarantees of PTM. So please refer to our paper on more optimization details, right? So overall, as we come to the end of this talk, in this talk I presented some of the key techniques in the TENET and what it entails in terms of memory safety and fault tolerance. In the paper, we do have a lot of insights to provide, and we do talk about a lot of challenges in terms of how the memory safety and concurrency are intertwined, and how the scalability, we preserve the scalability with our memory safety design, right? And we also talk about how we are able to guarantee memory safety for arrays, because guaranteeing memory safety for arrays has always been challenging in the research area. So that's something that we also discuss in the paper, right? So please refer to our paper for more details. Finally, in the beginning of the talk, we started by seeing how the NVM data is vulnerable to even a small trivial bug in an application, and also due to the hardware and device wear out, right? Because NVM is basically exposed directly to the user space, right? And there is no longer a file system or anything to protect as it used to be in a traditional storage media, right? So as a solution to this data corruption problem, we presented TENET here, which is a memory safety and fault tolerant persistent transaction memory, right? The key takeaway in TENET is how we are able to use simple and lightweight techniques like memory protection keys and canary bits and pointer tags to guarantee a robust memory safety, right? And as a result, we are able to design a practical system that focus both on performance, safety, and fault tolerance, right? Doesn't trade off one for other in a bigger sense. So overall, yeah, TENET guarantees a robust memory protection and fault tolerance at a modest performance overhead. And that's the end of the talk. Thank you for listening, and I'm happy to take questions.